Why soil resistivity data matters. Before an electrical earthing system can be installed, a few other activities should first be undertaken. Historically, installation companies may have offered to drive a single earth rod and take a range of readings from it at various depths as it is driven into the ground. But this is no comparison to the professional approach. The only thorough, scientific and logical method of determining an electrical earthing system is to undertake a complete soil resistivity survey to an approved methodology. How ground types influence electrical earthing. The material composition of ground masses varies from location to location. Furthermore, any given location is highly unlikely to have homogeneous composition, which is to mean that the material composition will not be uniform as a result of a range of natural events and human intervention. This table is drawn from BS 7430, which is one of the standards governing electrical earthing systems in the UK, and it is included to demonstrate the variances of ground resistivity subject to material composition. This table has been produced in an attempt to illustrate the variances between soil types, and it is not intended to be used to replace site testing and information gathering activities. What the table does demonstrate is the challenge in creating an appropriate earthing system for a given site. Beneficial salts and moisture content of a ground mass significantly affect moisture content of a given location, which in turn largely contributes to the electrolytic soil resistivity of that ground mass. Whilst temperature affects soil resistivity, it is only in frost-type conditions where its effect is notably negative, and as such, its influential contribution is deemed to only be applicable up to the first 0.5 metre below the ground. This is a major factor why electrical earthing systems are usually installed in the ground no shallower than 0.6 of a metre, and why systems shallower than 0.5 of a metre are usually dismissed as ineffective. Not only is a given site unlikely to have uniform material composition across its soil type, it is also likely to be subject to a number of different layers of strata. These images illustrate how the ground mass of a given area comprises different strata, each with a differing soil type. This concept of ground composition, coupled with a recognition that soil types conduct differently, convey how influential soil resistivity is on the effective distribution of electrical current passing through an electrode into that ground mass. The ground mass of a given area is likely to have formed through a plurality of natural events over millions of years, and more recently, human interventions. An example might be how many areas experienced glacial activity during the last ice age, which carved through terrain. In the time following the ice age, erosion resulted in many of these areas beginning to infill with deposited material. We continue to see natural events and human interventions impact the ground profiles of land masses all over the world, and this only underlines the importance of recognizing how such events are likely to impact a given area's resistance to electrical current when designing earthing measures. Human activity, particularly since the Industrial Revolution, has seen land masses change significantly. Every time a foundation is excavated and reinstated, every time an industrial area is decommissioned, every time a water level varies, it will all affect the way that ground mass will disperse electrical current and how hostile it may be to conventional earthing products. Human activity is one of the most important pieces of information to possess when it comes to evaluating a site's soil profile. To provide a shorter time-framed example, a common construction process that is frequently used when establishing a site is remediation, whereby a ground mass is excavated and essentially replaced with ballast-type material, which may provide greater stability for the construction activities to follow. That being stated, the ground mass that was previously present will discharge electrical current in a significantly different manner to the crushed rock, which is often used during remediation. As such, remediation activities should always be considered as part of the electrical earthing system design. The most commonly used method of undertaking a soil resistivity survey in the UK is the Wenner method, so much so that many parties are unaware that there are alternatives to it. It is a simple method, and if followed using a suitable test instrument and cable assembly, will provide an accurate indication of the apparent resistivity of the local ground mass. The Wenner method is based upon identifying a central position of the test. Here you will set up your test instrument. The method relies on 2 current probes and 2 potential probes set equidistantly and activated to obtain a measurement, and this is shown on the schematic through the notation C for the current probes and P for the potential probes. Therefore, working left to right, we see C2 being current probe 2 paired with P2 being potential probe 2. On the other side, we see P1 being potential probe 1 and C1 being current probe 1. The current probes are the point where electrical current will be injected into the ground, and the potential probes will measure the voltage loss for that given activation of the test instrument. This is why our current probes are located further away and the potential probes in the middle, as the activation point is measuring back to that central point. Spacing between the probes should be equal. For example, if the current probes were located at 3 meters lateral distance from the test instrument, then the potential probes will be located at 1 meter distance, resulting in 2 meters distance between each probe. Furthermore, the separation between the probes is the depth to which the electrical current will pass through the ground. As such, if there is 1 meter between the probes, then it will only go 1 meter depth. If you have 54 meters distance, it will go 54 meters into the ground. For a specific location, there may be in excess of 10 different activations, with each activation being a different distance between the probes. It is important to note that these tests should be undertaken in a straight line, otherwise the data will not be representative of the site. The equipment that you can access, buy or make will determine the process adopted on site. The photograph on the left demonstrates engineers using 4 test cable reels and 4 test probes, being earth rods, which reference 2 measuring tapes to verify the distance between the probes. The engineers will likely determine the furthest current probe distance required, install the current probes at that distance from the central point, and then install the potential probes at their respective distance. The test cables will then connect to those test probes, at which point the test instrument will be activated. Once the result from the instrument has been recorded, the test instrument will be deactivated, and the engineers will then move both sets of probes and cable reels to the next point along. This means that as the survey progresses, the test probes and cables will be getting closer to the central point. This sort of test takes little time to run the measuring tapes out and start obtaining results, but does require a lot of walking backwards and forwards moving the test probes. Furthermore, there is less weight than the other equipment discussed in a moment. For a given soil resistivity survey, we recommend a number of routes are adopted to ensure that the data is verified as representative, and where possible, that 2 test instruments are used for each activation distance to ensure that the test instruments correlate. Some companies do not reference measuring tapes, instead relying on engineers pacing out the distances, which is unreliable. Furthermore, some companies only undertake a single route, a further compromise as there is no verification of the data set obtained. Most companies do not use multiple test instruments. This is one of those decisions that engineers have to consider, as earthing services are often responsible for safety critical systems carrying potentially large fault current, and as such there is no advantage for us to take risk, because the consequences of cutting corners could result in fatalities. The second photograph demonstrates an engineer using application-specific manufactured test leads. These comprise multiple cables cut to specific test distance lengths, terminating in a connection point for the test probe. Multiple test probes are used here, with each distance of the test having its own test probe. The test leads terminate in a switch with the dial, whereby specific test probes will be activated to obtain a result for that specific distance. Earthing Services has adopted the second method. Whilst it requires more equipment and establishment time, it is faster to complete and rules out any induction interference on the cables. This sort of test equipment takes a little time to manufacture, but the time saved on site and the confidence in the data it provides justifies the upfront time and equipment cost. With regards to test instruments, Earthing Services uses mega products. These are not the only variety of products suitable on the market capable of providing a representative soil model, but they have proven their worth to us. In the event of any concern on the appropriateness of a device, feel free to get in touch to verify or get in touch with a reliable retailer. From the moment the company receives an order which requires a soil resistivity survey, Earthing Services engineers commence the desktop planning stage of the project. Our trained team knows how to assess the practicality and usefulness of a given area when it comes to undertaking soil resistivity surveys. And this can begin by using topographical data, location coordinates, and plotting technologies. In many instances, simply loading up Google Earth will give an idea as to viability of test routes. Although do remember that Google Earth is not live, and as such, do check that the areas selected remain valid. A single run or collection of soil resistivity data requires approximately 170 meters of uninterrupted open land, soil type ground mass. And this enables the engineers to assess the electrical resistivity attributes of the ground to a depth of over 50 meters. It is usual that the lower the depths, the more stable and generally better the electrical resistivity performance. In the event that less land is available, it is not uncommon to do shorter and therefore shallower soil resistivity surveys. However, this results in a less exhaustive data set. Due to the specific geographic requirements for undertaking soil resistivity surveys, there are occasions where this is unavailable at the project site and alternative locations have to be used. This may seem excessive, but if followed, it assures that engineers obtain accurate, meaningful data that will capture the subsurface electrical characteristics of a site. When determining a test route, ask yourselves these questions. Is the length sufficient for a test? Is the terrain appropriate? Remember, you have to be able to hammer test rods into the ground, so tarmac, concrete, or similar will not allow this. And ballast type will likely have too many air gaps to ensure good contact is established to the test rod. Are there underground services or tree roots? The presence of these will distort the test results. Are there any other groundworks or explosions being undertaken at the time of test? Groundworks and explosions cause vibrations in the ground which will distort current flow. Is the route accessible with the equipment you will be carrying? And if the answer to these questions is all positive, then the route seems viable. When the engineers arrive at site, they may well have to be inducted, receive a briefing, or hold a meeting with the client's representatives. And all of the time, they will be evaluating how the activity on site, both current and historic, may have impacted upon the substrata. Prior to setting up the first soil resistivity survey location, it is common for Earthing Services engineers to visually inspect the area, including assessments on local flora and fauna. Mature trees or subsurface agricultural elements can distort or bias electrical resistance within the ground, and as such must be avoided, and reading the landscape is always informative. Whilst the testing stage is notionally the main event, without thoroughness at each stage leading up to it, and indeed following it, the soil resistivity survey data may be insufficient to confidently specify an effective, safe electrical earthing system. Follow the method, keep the cables in a straight line as far as possible, make sure your test probes have good contact with the ground, and you should find it provides a solid data set. Once you have done a couple of these tests, you realize how easy they are and how beneficial the data it provides is. We will be moving on to processing data in a moment. It is worth acknowledging that if you do not have access to the software to do this, then you can always contact Earthing Services. There will be a small fee associated with processing the data, but we will certainly do it for you. So far, we've had a lot of talking and not enough evidence of importance. So let's run a case study and see whether obtaining soil resistivity data would be useful or not. This table of data was obtained from a test location in the southeast of the UK. This testing was undertaken to provide an evaluative model as part of product testing, where the commissioning party was comparing the performance of a number of electrode types and configurations. For their evaluation, 5 conductor variants were installed, and this was done prior to processing the data set obtained from soil resistivity testing. If we consider that so many people install earthing components blindly, both in terms of driving rods into the ground, which is blind even if scanning has been completed, and blind in terms of knowledge of how well the ground mass will handle electrical current. You will see that 3 different locations were used to obtain representative data for the site, although that at location 3, data was not obtained the longest and therefore deepest depths due to site constraints. However, location 3 was the most proximate to the installation site of the various electrodes under test, being directly above the excavations for the electrodes. Whilst land masses are unlikely to yield dramatically different soil models over a short distance, if exact locations are possible, then that is preferable. This demonstrates the test results plotted on a graph, which shows a commonly observed trait. For a given area, the deeper into the ground you test, the more likely the results will be consistent. This is partially a consequence of a lack of human interference. After all, humans usually do not disrupt ground to depths of 54 meters. Whilst testing to 54 meters may seem excessive, most UK distribution network operators will insist upon that scope of testing. Furthermore, even if you are installing something near the surface, the deeper layers will still have an impact on performance. Identified disparities on some of the test data were extracted from the data set, with the location 3 data verified to be accurate for the purposes of analysis. We use a suite of software when processing soil resistivity data called CDEGS, which is the industry standard earthing system software that is used globally, the accuracy of which is largely uncontested. To be clear, if an accurate soil resistivity survey has been undertaken, and as long as the installation is effectively completed, then an earthing system designed by CDEGS is likely to be within 0.1 of an ohm of the final system test. The table evidences the soil model obtained when this dataset was processed, which indicates a significantly high resistance top layer, which descends some 400 millimeters from surface level. The table evidences the soil model obtained when this dataset was processed, which indicates a significantly high resistance top layer, which descends some 400 millimeters from surface level, between 400 millimeters beneath the surface to a depth of 2,540 millimeters from surface. The resistivity drops from 277.99 ohms to 18.66 ohms. That second layer being only 6.7% of the resistance of the top layer. Try and keep this in mind when we look at the next slide. This graph shows the performance of the 5 conductor variants when tested over a period of time. All of the variants are either the same specification of conjudisc, albeit one encased in conducrete, or the same specification of earth rod. So which is the best performing conductor? If we draw our conclusion as to which is the best performing conductor on this graph, then the yellow line, being a vertically installed earth rod, is the lowest apparent resistance, therefore notionally best performing conductor. Second place will go to the red line, being the vertically installed conjudisc. These results were quite surprising. There are 3 variants of one type of product and 2 variants of another type, and yet performance notably differs. Based on the specification of the products alone, the conjudisc should be lower than the vertically installed rod due to its greater contact surface area, being 3 times that of the earth rod, and lower inherent resistance. Why would a horizontally installed earth rod be so much worse than a vertically installed rod? Why would a vertically installed conjudisc be so much better than a horizontally installed conjudisc? On face value, the process of driving an earth rod ensures good contact with the ground mass that is being forced into the ground, whereas a horizontally laid earth rod wouldn't immediately have that, as there is no force required to install it. But that alone wouldn't explain the huge difference in performance. Furthermore, none of the conduits were driven into the ground, so that explanation does not work for all of those. What's the hidden factor? However, think back to the differing soil model, which is the pertinent factor when considering that of the 5 electrode variants under test that were installed blindly, that 4 of them were located almost entirely in that layer of high resistance, with only 1 penetrating the dramatically lower resistance of the layer beneath. Let's visualize that concept. As already stated, the conductors were installed in different soil strata with significantly different apparent resistivity, as we can see here. The top layer, where 4 of the conductors are partially or entirely installed into, has an apparent resistivity in excess of 277 ohms meter. The only conductor installed entirely into the second soil layer with an apparent resistivity of less than 19 ohms meter is the vertically installed earth rod. This goes some way to explaining why there is such a disparity in measured performance against expected performance based upon the attributes of the conductors in isolation. As further installation or testing at the test site was no longer possible, seed eggs was used to simulate performance if the conduit had been entirely installed in the same soil layer as the vertical earth rod. The table at the top of this slide is the data we saw a couple of slides ago, only on that occasion it was presented as a graph. The best performance observed for the vertically driven earth rod was 24 ohms, whereas the best performance for the vertical conduit, being the conduit variant partially exposed to the same layer as the driven earth rod, was 26.2 ohms. CDEX confirms that the conduit installed entirely in the same layer as the driven rod would achieve a resistance of 9.8181 ohms, being less than half the resistance of the earth rod. This calculated performance aligns with the product specification and observed values in countless case studies. When the vertical earth rod was simulated based upon proportional exposure to the higher resistance layer, its performance dropped dramatically. So when asking again which is the best performing conductor, the answer is the conduit. Not only did it achieve near parity performance, despite being exposed to a significantly higher resistance layer, it was a far safer and easier install to complete. Here we see the test location plan and on-site verification for suitability. As there were no obstacles, the planned routes were used. Furthermore, as the ground was flat, directly over the installation location, and the dataset correlated, there was no need for any further testing activities for this project. As you can see from these 2 tables, the 2 test runs, each using 2 test instruments, yielded 4 comparable datasets. The test runs went through the first stage of processing, and then were processed through CDEGs to yield a combined soil model to be advanced towards design. Again, to restate what we saw previously, this model indicates a high resistance layer up to 1 meter depth, followed by a significantly lower layer of just over 15.5 meters in depth, before again seeing a higher resistance. Also to restate that the thickness of layer 3 being nominally infinite simply confirms that no other layers were detected to the depth of the testing activities, which in this case was 54 meters. Therefore, the 54 meters tested, these were the only layers identified. So now we know how the ground mass will discharge electrical current. But what fault level might the earthing system have to manage? This sort of information is provided by the respective DNO. In this instance, the DNO advised that the maximum 3-phase fault level was 13.122 Ka, the 1-phase fault of 2.605 Ka, with a fault clearance time of 1 second. However, the fault profile must consider the whole circuit. As such, it was verified that the site was connected to an 11 kV primary substation via 2 circuits from feeder 1 and feeder 2. Both circuits were 300mm triplex cable, 0.8 of a kilometre in length. These inputs fed into our calculations to determine the fault that the site would feasibly carry. The output of the calculation suggested 912 amps would be the appropriate level to carry out all touch, step and transferred voltage assessments. Earthing conductors must be selected from standard copper section, which has to carry the full fault current from the point of fault to the main earthing system. It is recommended that the value of current rating to be taken is that corresponding to the ultimate system maximum symmetrical 3-phase short circuit current. Subsequent redistribution of these circuits into 2 or more paths allows a reduction in the size of the branch conductors. To restate, in this example, the maximum 3-phase fault was 13.122 Ka. The 1-phase fault was 2.605 Ka. The fault clearance time was 1 second. Detailed within Energy Networks Association Technical Specification 4124, Guidelines for the Design, Installation, Testing and Maintenance of Main Earthing Systems in Substations, is the formula for determining the current density of earth electrodes evidenced in these calculations. The earthing system design had to comply with all relevant standards and project specifications. Due to a combination of a high 1-phase earth fault and a high soil resistivity soil model, an extensive earth is required to ensure the site is classified as a cold site. A cold site relates to a return of earth potential, ROEP, of less than 430 volts. Anything exceeding this would be considered a hot site, which may require additional steps are taken relating to separating HV and LV earthing provisions. The earth system comprised a series of horizontal and vertical electrodes. The horizontal electrodes were 120mm square hard-drawn bare cables encapsulated within conducrete and reinstated with native soil. This conductor needed to be installed at a depth of 1200mm to ensure it was placed within the lower resistivity layer that we would only have known was there due to the soil resistivity survey undertaken. Attached to the perimeter grading electrode were 11 number 10 meter by 120 millimeter diameter boreholes filled with conducrete conductive concrete. The depth ensured the electrodes sit within the optimum soil layer. Included within the design were connections to each foundation reinforcing to form an electrical circuit throughout. Earth bars were specified within the substation and the transformer room to facilitate earth connections for the main plant of this facility. The theoretical earth resistance of the earthing system, determined by the CDEG software, was 0.453 of an ohm. Touch potential is the voltage between an energized object and the feet of a person in contact with that energized object. It is equal to the difference in voltage between the object and a point some distance away. The touch potential or touch voltage would be nearly the full voltage across the earthed object if that object is earthed at a point remote from the place where the person is in contact with it. For example, a crane that was earthed to the system neutral and that contacted energized line would expose any person in contact with the crane or its insulated load line to a touch potential nearly equal to the full fault voltage. This table within Energy Networks Association 4124 provides indicative permissible touch potentials in relation to ground surface type and exposure times. This plot indicates the calculated touch potential in the event of an earth fault. The plot below is based on a percentage of the EPR, being 5.01% of 413 volts equals 20.01 volts, which is within the limits as indicated previously. Step potential is the step voltage between the feet of a person standing near an energized earth object in this case, the earthing system under fault conditions, it is equal to the difference in voltage given by the voltage distribution curve between 2 points at different distances from the electrode. A person could be at risk of injury during a fault simply by standing near the earthing point. This table within Energy Networks Association 4124 provides indicative permissible step potentials in relation to ground surface type and exposure times. This plot indicates the calculated step potential in the event of an earth fault. The plot shown is based on a percentage of the EPR being 6.97% of 413 volts, which is 28.79 volts, which is within the limits as indicated previously. If you think of the radiating electrical energy within the Earth during a fault current event, you must consider the consequence of what it might interact with. Should the discharging current encounter a more conductive medium, it is likely to discharge through that instead of the ground, as it will provide a path of lower electrical resistance. This can have significant consequences if the item through which the fault current is now flowing is a sensitive system. When professional electrical earthing system designers specify an electrical earthing system, they determine how far and at what volume fault current is likely to travel. This calculation is known as identifying the return of earth potential, ROEP. Ensuring that the ROEP does not threaten adjacent structures or infrastructure is an important responsibility. A cold site relates to requirements in Engineering Recommendation S36 Issue 2, 2018. A return of earth potential, ROEP, of less than 430 volts can be considered cold. Anything exceeding this will be considered a hot site, which may require additional steps are taken relating to separating HV and LV earthing provisions. The ROEP in this case study was calculated at 413 volts. Therefore, it's classified as a cold site. Thank you for your attention throughout this time. It isn't an easy subject to take on board. When it comes to electrical earthing systems, there are several factors which will determine how well it works, being the resistance of surrounding mass of earth, i.e. how well it discharges electricity, the inherent resistance of the conductors, i.e. how well the conductors discharge electricity into that surrounding mass of earth, the contact surface area of the conductors, i.e. how much conductor interfaces with the surrounding mass of earth, the total discharge zone of conductors, i.e. what's the footprint of the conductor network, and the resilience and longevity of the conductor network, i.e. how reliable is that conductor network on an immediate and long-term timescale, meaning the conductors work today, will they tomorrow, will they in a decade, and so on. So, how resistant is the ground? How much of it can we use? What conductors will we put in it? In what kind of orientation? And how much of the conductors are there? The first step is the soil model. And if we do not know how well it discharges current, everything after it is speculative. And remember, electrical earthing systems are life-saving systems. If you get them wrong, someone could die, be it through direct shock or critical equipment failures. When it comes to soil resistivity surveys, our advice is to take the time to do it right. And remember, if you have done a soil resistivity survey and need the data processing, please get in touch with Earthing Services, and we will do that on your behalf for a small fee. Thank you again for your time, and feel free to get in touch with any questions. Thank you.